All right, 4.6, applications and models of exponential growth and decay. So essentially these are just like some word problems to apply what we've been doing in this chapter. Pretty easy. I'm basically just focusing on like a couple of the like really common ones that you would have, to where if you went on to pre-cal next year, you'd have seen it at least a little bit. There's still not like a ton that we do with it in pre-cal, but we do a little bit more than we do in here, but that way you have a slight introduction to it in case you end up going that route. So, to start out with, we are going to look at finding doubling time for money. So a formula that we're going to need is the continuous compounding formula. Which is A equals PE to the RT. And there's a lot of different like money formulas, but this one involves E, which is why that would be in with the exponential growth and decay stuff. Like using logs to solve depending on what we're trying to solve for. So the problem, and there's not like a ton of like good examples in the book, so some of these I just tried to find one that was similar so that when I give you a couple, like you'll have something that you can do that's like it. So how long will it take for money in an account that accrues interest? Y'all probably know this, but accrues is just like earns interest at a rate of 3% compounded continuously to double. All right, so obviously in here, some things, it says it's compounded continuously, which I'm just pointing this out because, again, like I said, there's other things like we can have, like at some banks, your money is compounded quarterly, sometimes it's monthly, it just depends, and they have like obviously their different rates and stuff, so you can actually figure out like if you put money in, you could actually use like these formulas, which not this one because pretty much nobody's continuously compounding anything at any bank that we're probably dealing with, but you can use the formulas and stuff to figure out like how much, like how long it's going to take for you to have X number of dollars in your account if you have an interest rate of whatever the rate is, which is pretty cool. But anyway, so that's essentially what we're looking at here. So how long will it take for the money in an account that accrues interest at a rate of 3%? So this is R for rate, but we have to convert this to a decimal. So what is 3% as a decimal? 0.03. Yep, so 0.03. Compounded continuously to double. So that's the other thing we want to note there, is that we're trying to double our money. So the initial amount that's put in, or the principal, is the P, okay? So obviously they didn't tell us exactly what that is, but we just want to know how long it will take our money to double. So if we want double what our principal was that we started with, we're going to call the amount that we're ultimately trying to get to 2P. So it's going to be 2p equals p. Now, e is just a number. And then that's raised to 0.03. Turn this off before it tries to solve this equation. And then we want to know how long it'll take. So they didn't give us that, so I just put t there, and that's what I'm going to be like solving for. What is happening? Go off. Okay. All right, so I need to solve this equation just like I would solve a normal equation. There are multiple things that I don't know here, right? I don't know p and I don't know t, but I'm trying to solve for which variable? T, yeah, for time, because it wants how long will it take. So I'm solving for t. So if you want to note that, t is what I don't know. So I'm going to divide both sides by p because p is being multiplied by this, and I need to get this piece by itself. So when I divide by p, I get 2 equals e to the 0.03 t. Now, when we were solving equations, what was that, yesterday? I don't know. Was that yesterday we were making the L, or was that last week? I don't know. Anyways. But we're going to we have an exponential. I need a log to solve it. So I need to actually move this equals 2 to the other side so that I can do it, because I can't do it when it's written on the left-hand side. I need the piece with the variable on the left. So I'm going to change this and just move the equals 2 over here. So I'm going to make the L, so I come down through here, up and over. So this is log base E, or we know that to be ln of 2 equals 0.03 t. And then I'm going to divide by 0.03. So ultimately, t equals the ln of 2 over 0.03. Here's calculator's all the way over here. So then I just type that in. Ln of 2 divided by 0.03 gives me 23 point, let's just say 1 decimal place, 0.1 years. Now, 3%, well, it's actually not too bad of an interest rate, but to like completely double your money, that, I mean, it does, obviously is a long time, but things to think about when you're choosing what your savings account is going to be, of who can I get the most like savings with, or like get the most interest with.
Is that for any amount of money that you put in?
Mm-hmm. But this one's also being compounded continuously. So that basically means like essentially like it's like almost like daily they're like putting interest on it. So like every time, but like you have to think like 3% is literally only like 3 cents on every dollar. So
if you put $1 into this account, it would take 23 years for you to get 2? Or would it be?
Well, we can actually check. Let's see. Because in theory, if we plug this number in and we want this to be $2, let's see what happens. It seems kind of weird to think that that would be the case, but yeah. When I plug this in, I get that A is equal to 1.9997. So yes, $2. So it really does. It's kind of crazy. He doesn't know how to feel about that.
I don't know. If you put in $1 million, it would take the same amount of time for you to get to 2 million. That doesn't seem right.
Well, you got to put more in to get more out.
I feel like if there's less money, you should get more interest.
Well, let's do another one. Let's do $1,000. Some do, I think. Like, I think some banks do say if it's like this amount of money, you get this much, and then at like this much, you get this much. But that's why they also offer things like those, you've probably heard of them, like CDs. Which, like, I still don't understand, like, what an actual CD is. Because somebody was like, yeah, it's literally like a CD, like a disc that you, like, get, and it has money on it. And I was like, but how does that work? Like, I don't understand. Like, I understand how you get the money back. But, like, they're like, yeah, it's like an actual, like, disc. And I was like, I just don't understand that. Like, that's super weird. I don't know. But a lot of times those things, you put money in there, but you can't touch it until it has, like, it's, I forget what the name of it is, but it's, like, finalized. Like, so if it's, like, a 5-year CD, you put your $500 in, and then, like, you don't get the money back until, like, that 5 years is up. But, like, you know, like, okay, I put in this much money, so at the end, it's going to be worth this much.
Well, what if you lose the disc?
You don't. Like, it stays at the bank.
Oh, okay. I thought they would.
Typically, like, the bank will hold on to it. Like, you may have something that you take with you to, like, show that you have it, but, like, you can't, like, take that back, if that makes sense. Like, you don't just, like, get your money out. Like, I'm sure there's, like, extenuating circumstances, but I think the deal is, like, if you say, like, it was for 5 years, and after 2 years, you're like, I desperately need my $500 right now, like, I have huge car repair, and I don't have, like, extra money to pay for it. You can go, I think, get your $500 back, but you don't get any of the interest that would have been on it. And stuff like that. So, like one example, like, my cousin, her grandpa was super sick and was, like, pretty sure, like, he wasn't going to make it to see her graduate, and, like, she's just a freshman in high school, and he didn't. But when her sister graduated from high school, he had them both come over, and he gave them both their graduation gift, but hers was under the stipulation of you can't use this until you graduate. Well, she got it when she was in 8th grade, and so she went and bought, like, a 5-year CD with it, and so she'll actually end up with more money by the time it's all said and done, because when she graduates, it will have accrued all that interest and stuff like that. Which I thought was really smart. I was like, I probably would not have thought to do that. I probably would have just shoved it in the bank account and just not touched it. But she was like, that way I can't touch it for any reason. Because she's like, I want to honor that, like, what he did. So there's, like, I mean, obviously pros and cons to it. But if you can do something like that, it can be really smart too. So good way to save money. But oh, let me type this one in and see what happens. Yep. This is $1,999.71. I mean, basically. And I will say, the reason that this isn't coming out to be exactly 2 and this isn't exactly 2,000 is because I'm using a rounded number here. If I was using, because this decimal was actually 23.104900602, and it keeps going. But that's all I can see on my calculator. So if I use that exact number, then it would come out. So, like, let me see what happens if I do that. Oh, that's not the right button. Yeah. If I use this exact number, it comes out to exactly 2,000. So, yes. Kind of crazy, but yes. Things to think about, though, as you get older and have jobs and start saving money. Where am I going to get the most back for my, like your typical, like say like a Wells Fargo, you get like nothing. Credit unions, you typically get a little more. Like they usually give you a little bit more, but it's only on savings. Usually, you don't usually get anything on checking. On rare occasions, you might, but it's not often. But then there's other things like Discover, for example, like the credit card company. They also have a savings account where you make a insane amount of interest. Their interest rate is like 4%. And most banks are probably like a Wells Fargo is probably 1% or less. A credit union is probably like 2% or so. I mean, and it's public, like you can see what their rates are, but it's insane, like to like look up, and I don't know what all the different ones are or whatever, but somebody had told me about Discover, and it's true. I didn't know if I would believe them, but it's true. Like, so definitely worth looking into as you get older, of where can I get the most for letting them hold my money, basically. So. All right. Any other questions on that problem? All right. The other type of problem that we're going to deal with is population growth. So, according to the U.S. Census Bureau, the world population reached 6 billion people during 1999 and was growing exponentially. Also, just for reference, when y'all are actually doing these problems, you don't necessarily have to write the whole problem out if you want to, so that like you have it for reference and you can like mark on it. Obviously you can, but I don't require you to copy them down because they can be kind of long. By the end of 2010, the population had grown to 6.947 billion. The projected world population in billions of people T years after 2010 is given by the function f of t equals 6.947 e raised to the 0.00745 t. So then this question's done in two parts. So A, based on this model, what will the population, oh, this is interesting. What will the population be in 2025? We'll have to go back later at some point and look and see. I got one of those census survey things. I think it took like an hour to fill out. I thought it was just going to be like how many people live in your house. No, it's not. I was like, this is absolutely ridiculous. Like, it wanted so much information. I was like, I thought the point of a census was just to know how many people, not like how old my house is and like how many cars I have. And I was like, why? I don't understand. Probably so they can do things like this and put them in a math problem. Like, there's a problem we do in physics that we try to estimate how many gallons of gas are used in a year, like in like the US. What you obviously have to do a lot of assuming, but we've kind of tried to like look up before and see like how close we actually were, which it's so hard now with like all the different kinds of cars and stuff like that, because like an electric car obviously doesn't use gas, but like you have to count those cars when you're like counting how many cars, and I don't know, it gets to be a lot. But anyways. All right, so essentially, the first chunk of this information about the population during 1999, not really useful to us for this particular problem, as far as that goes, because they then go to 2010, tell us that population, and then they give us a formula based on 2010. So, like, really not super useful for us to have the stuff about 1999. More just informational. So we have this formula that we're going to use, and it's T years after 2010. Okay? So that means that the year 2010 is year 0. Because that's like the initial. So if I plugged in 0 for T, that would be e to the 0, which is just 1, which gives me 6.947. Okay, so that's where we're getting that from. So, but T is the years after 2010. So how many years after 2010 is the year 2025? 15. So 2025, T is equal to 15. So now, essentially all we're doing is we're taking this formula and plugging in 15 for T, and we will have what our projected population will be for this year. So f of 15 equals 6.947 e to the 0.00745 times 15. And then I just type that in. 6.947. Almost hit the wrong button again. E to the 0.00745 times 15. And so in the year 2025, that is going to give us I guess since they did 3 decimal places, we'll do that. 768 billion people. So it'll be curious to see if that's accurate or not.
I think we passed 8 billion.
That's what I thought. I thought it was like somewhere in like the 8 range.
So we're a little bit.
It's always interesting to me though, because it's like, I don't know. Maybe I just like think about it too much, but like I feel like at some point the number should level, which I mean exponentially that kind of would be true, I guess. But like I feel like because people die every year and people are born every year, and I would think they would be a similar quantity of people dying and being born every year. But I guess maybe not. I don't know. I've tried to like understand before how like the population can change like so drastically. I mean, I guess year to year maybe it doesn't, but like over time, like this is over 15 years. In theory, like we're almost a billion more, which obviously if the 8 billion is right, then we're over a billion more from, in theory, 2010. And this is just also assuming that these were accurate numbers. I mean, I'm assuming they are since they're saying it's from the U.S. Census Bureau, but I take it for what it is because it's a math book, so who knows where they got the numbers from. If it was in my stats book, I would think maybe it's a little more serious, but. Now, part B. If this trend continues, approximately when will the world, I keep forgetting the window's open and I'm like, why can I hear things so vividly out there? When will the world population reach 9 billion? All right, so basically, kind of like the money problem when we were plugging in, we're going to be plugging in 9 billion for like the f of t in this original function that they gave us, and I'm solving for t. Now, because I know that ultimately I'm going to need this stuff on the left, I'm going to actually put f of t on the right, but just purely a notation thing. So I've got 6.947 e to the 0.00745, and now I'm trying to figure out when this is going to happen. So I'm going to put just t here equals 9. So first thing I'm going to do is divide by this 6.947. So e to the 0.00745 t equals 1.296. And that number keeps going. I've rounded it. So now we have an exponential. I'm going to use a log to do it. So this is going to be the ln of 1.296 equals 0.00745t. So I'm going to divide this number by this. So the ln of 1.296 divided by 0.00745 is 34.803. So now this is t, but t represents years past 2010. So any idea what I might need to do? Well, sorta, but I already kind of did round. But if I want to know what year this happens, what do I need to do? If t was years since 2010.
Add it to 2010.
Yep, so I'm going to do 2010 plus the 34.8. I'm just going to say that. So that means that this will be the year 2044. So basically during the year 2044, this will happen. If we wanted to go crazy, we could actually figure out exactly what month in theory this will happen by converting the rest of this to months, but that's excessive. But during the year 2044, in theory, we will hit 9 billion people. So in 2024, or 2044, not 2024, 2044, we'll have to see if it's actually 9 billion. I feel like we might hit that before that if we hit 8 billion last year, but
Definitely.
we'll see. Who knows? Any questions on that? All right, so problems for you then are 31 and 32. And if we need to go over these tomorrow, like if y'all get stuck or something, but 31 and 32 are the interest problems. They kind of go together actually. And then a population problem, number 38, but just part A and B. And when it says like to the nearest tenth of a year, that just means like 1 decimal place is what they're looking for. That's all that they mean by that. But just those three, and that's it for this section.